So I'm talking to you about sea level rise in Virginia, but also about the problems that this is causing with our infrastructure. And in this case, I'm focusing mostly on our infrastructure that we find in our rural areas, which is a little different from what we find in the urban areas. This is, although this picture is from an urban area, this is from downtown Norfolk on a nice sunny day, and you can see the water is approximately 3 blocks from the actual shoreline in this picture. So this is something that's happening more and more frequently, and we're going to talk about that a little bit, but then also what are the implications of that for our other systems. I'm part of the Center for Coastal Resources Management at VIMS. If you're not familiar with the Center for Coastal Resource Management, or CCRM, we were developed specifically to do science that is related to the management of our coastlines. So what I'm showing you today is a small portion of the work we've done. We're a large group, there's 22 people, and we have 40 years of doing different projects and that kind of thing along the coastline. So if you're interested in other things, I have our website will be at the end, and you can go and poke around and see what other kinds of projects we've done. Okay, so we wanted to talk about why that flooding is becoming a bigger and bigger problem. So this graph is from tide gauge data that my late colleague, Dr. Larry Atkinson, compiled for me. And it's showing the hours of flooding in Ghent for every year since 1928. And so what we can see is that between 1928 and 1960 kind of time, flooding doesn't happen that often in Norfolk. It just occurs occasionally. We have these 2 years where you had more than 50 hours of flooding in them in the entire year, though, and probably associated with big storm events. If we move forward to the 1980s, what we can see is that we still get these periodic years where we have more than 50 hours of flooding. Flooding, if we look at it really hard, we can see that it seems to be flooding more on this end than this end, but not really in a way that people would notice in their experiences. And we have this 1 year at the very end of the series where we have more than 3 days, more than 72 hours of flooding in that year. So that's our worst year. Okay, so if we move forward, this goes out through 2012. What we can see is suddenly the flooding gets much, much worse. And in fact, so this red line is our worst year of flooding before 1985. And by the 2000s, this is actually looking like a pretty good year. If that's all the flooding we get, we feel pretty good about that. So what's been happening here? Part of it is that sea level is rising, and not just rising, it's actually accelerating how fast it's rising. So it's coming up a little bit faster each year than it did the year before. The other thing that's happening is that we've just reached an elevation. Our land right along our coastline is typically very, very flat. And so we've reached this point where the water is coming over onto that land, and it can go fairly far inland because the land is so flat. So we're having water coming up, and we're also at an elevation where we're just experiencing longer flooding. The problem, of course, is that a lot of our infrastructure was built in the 60s. A lot of our lots were platted in the 80s. So we did a lot of our development in a sort of different era than what we're experiencing now. Okay, the other thing that's changed, and I just want to mention this, I'm not going to talk a lot about it, but it is, of course, contributing to flooding problems, is an increase in rain intensity. And these are intensity, duration, frequency curves. So how heavy the rain is for how long, okay? And this red one is the Atlas 14 IDF curves. These were based really on old data from the 60s through 80s kind of. And this is what we expect to see from this point until for the next 50 years. We expect to see a higher IDF curve. So one of the things this is really impacting is stormwater drainage, of course. So again, most of our systems just are designed for this curve, and now we're experiencing this curve. When we get these high tides and they backwater up into either stormwater systems or they backwater up into the ditches, the roadside ditches, then of course the capacity of those water conveyance systems are reduced even further. And so we get this intense rain and we have reduced capacity. And so we get we get standing water in our ditches, we get water spilling over into people's yards. Where there's sewer systems, we sometimes have water coming up out of the sewer systems. If you're interested in seeing this, this is a tool from MARISA, which is a Mid-Atlantic NOAA-funded collaborative among a number of different universities. VIMS is the furthest south university, and the website is down here at the bottom. Okay, so sea level rise around the bay. So we frequently work with the Norfolk tide gauge, which is not right in the Middle Peninsula. So I just want to show you what this looks like around the bay. So this is Norfolk, and this is the Yorktown gauge, Solomon's Island, Maryland, Annapolis, and Baltimore. And we can see that the rise is highest in Norfolk and lowest at Baltimore, which makes sense because Baltimore is up near the Susquehanna River, where you get a lot of river influence. It's very far from the mouth of the Chesapeake Bay, so you get less of the ocean influence. However, Yorktown and Norfolk and Solomon's Island are actually very, very close. They're all over 5 millimeters of sea level rise. So although we typically use the Norfolk gauge, actually you could use any of these gauges and get perfectly reasonable planning results. Down here, I've put the Norfolk, Virginia gauge. And when you look at this, these blue lines with the little dots at the top. So this is the measured monthly mean sea level from the Yorktown gauge. So that's data that comes from the gauge. This goes back to 1969. This blue line here is what we call a decadal trend. And what you can see is it roughly follows patterns rising and falling of the high tides basically within any given year. And then the orange line is the trend line through the middle of that decadal signal. So we can see how that is changing over time, even though there's ups and downs in any particular given year. There's an overall trend. And we can take that trend line out to 2050, and we can see that it's looking about a little over 1.5 feet, 1.7 feet of sea level rise over our current tidal datum, which is close to 1.7 feet in a VD88. Okay, it's not exact, but it's pretty close. So that's the average that we expect to see out in 2050 in this area. I do want to point out these, I've lost my mouse, okay. These dotted lines here. These are the bounds of the expected variation. So you see how we have these monthly mean sea levels go up and they go down. So 95% of these monthly mean sea levels fall between these two dotted lines. So what we know going out into the future is just like this orange line trend line here is an approximation of what's actually happening in a given month. This orange trend line will be an approximation of what happens in a given month. So there will be months where we expect water in 2050 to be as high as 2.2 feet above NAVD88. And then there'll be months where we expect it to be just a foot above NAVD88. But the average is going to be about 1.5, 1.7 feet. So I did say, I want to point out that these are rising currently around 5 millimeters a year. I said that sea level is accelerating. What that means is that by 2050, they'll be rising more like 10 millimeters a year. So every year, right, rising a little bit faster. Okay, and then if we want to look out beyond 2050, we need to use global climate models. So the data I've been showing you is this is what's been happening in the past. If we assume that the future will be like the past, this is what we'd expect to see. However, there are a lot of reasons why people think the future might not be like the past. So moving out, we need to use global climate model derived curves. So these are the NOAA 2017 curves. You may have heard that NOAA recently came out with a set of 2022 curves that are don't have this extreme, and they're a little more tightly compressed around kind of this average. But they still, the historic trend is still going up the middle, basically, of what the 2022 curves show. Just like here, it's kind of going up the middle of the scenarios that are expected. So the important thing here is that there's a lot of potential uncertainty in 2021, anywhere from 2 feet of sea level rise, which we're not really expecting because these curves are below what our historic trend has been. But anywhere from 2 feet of sea level rise to 11 feet of sea level rise. The state had selected the 2017 curve, 2017 intermediate high curve as their planning curve, which gets a little above 6 feet in 2100. Okay, so the problem is Virginia actually has one of the highest rates of sea level rise on the East Coast. The only places with higher rates of rise are on the Gulf Coast. And many of the rural adaptation measures that we take, so elevating houses, redigging wells, rebuilding septic systems, have some limitations. So first of all, they place the entire cost of the adaptation on the private property owner, unless there's some, targeted funding that's available. And secondly, they direct, because they put the cost on the private property owner, they direct available resources towards short-term solutions. So one of the things we are hoping to do to help build the resilience of our coastal area is to start thinking more systematically about what the issues are. So it's not where one person's well fails and they deal with it, but actually all their neighbors' wells are failing too, and maybe there's a better systematic solution to it. Okay, so I'm going to talk through a couple of different issues and show you where resources are. You can learn more about them. So property flooding, this of course has become a big issue. This is Gwynn's Island from our Adapt VA interactive map. And if you look at, this is 2020, the blue is the edge of the water, the mean high water. So this is as high as we would expect water to get on a daily tide. By 2050, we starting to see some residences flooded, not terribly bad. By 2100, half the island is underwater. So we've got a long time to deal with the 2100 problem. The 2050 problem is relatively moderate in terms of flooding houses. Of course, as these properties flood, though, everything else on the property floods. So our roads, our septic systems, our well water, all are also seeing those impacts, and sometimes earlier than the parcel itself is flooding. Okay, so the tricky thing about planning is we're looking at those 6 scenarios that NOAA put out in their 2017 report, right? Okay, so this is a set of parcels, and you can see, okay, we have this parcel, so this is our best case scenario. So this is the low scenario. So this is the best case scenario we would expect flooding wise in 2050 for this area. And this is the worst case. This is under the extreme scenario. So we can see we have these parcels here with the green arrows are parcels that are likely to be underwater regardless of the scenario we're looking at. So we know these are areas where we want to plan to deal with the water. We see these parcels out here are unlikely to be underwater under any scenario. So these are parcels where we, if we wanted to put in a shopping center, we wanted to put in more residential or that kind of thing, these are areas where we can feel pretty comfortable we won't be dealing with water issues down the road. Now, the really hard areas are areas like these with the blue arrows, where under one scenario, they are not underwater, they're unlikely to flood. But under the extreme scenario, they're likely to be completely underwater. So planning for these is really difficult. And there's not really a good solution to it except to keep in mind that these areas are hard to predict what the outcome will be. And so as we find solutions for these areas, we want to remember that those solutions should be maybe more on the temporary side, that we need to keep that kind of temporary perspective in mind. Okay, so now I'm going to talk about road flooding, and I'm going to show you this road flooding tool that we have up. And this is the bar across the top of the tool, which I'm going to show you in a minute. But I wanted to show you this because when you open the tool up, it defaults to the Eastern Shore section. And so some people think this tool is only available for the Eastern Shore. However, it's just that there are regional tabs. And so you need to find your Middle Peninsula one and click on it. And then you can go in and look at the road flooding. Okay, so this is what the tool looks like. You can put on like land parcels and that kind of thing. These are showing roads which are inaccessible at different flood levels. So the colors tell you at what flood level. So at less than a half meter of flooding, these purple areas become inaccessible. And we'll zoom in a minute. And these red areas don't become inaccessible until there's 2.5 to 3 meters of flooding. These are done using a road network analysis, which is the same type of analysis that Google uses when you ask for directions, and it tells you the best way to get from one place to another. So these all have to have a starting point. So for the starting point for each locality, it is their locality seat. So it's saying, can you get to this point, to this road from the locality seat, given different levels of flooding? And then across the bottom, you can see this is for all of the Middle Peninsula. You can actually pick locality by locality if you want with the tabs. So for all the Middle Peninsula at a half meter of flooding, we have 10 miles of roads that are inaccessible. At 3 meters of flooding, which would be a really bad storm, a really, really bad storm, because that's 9 feet of rate of flooding, we have 825 miles of roads that are inaccessible. And then we've put here, just so you can see that this is what we expect sea level to be on the state planning horizon by 2050. So by 2050, we would expect about 170, maybe 150 miles of roads to be inaccessible. By 2100, we're looking at about 480 miles of roads being inaccessible in the Middle Peninsula. I want to just point out the difference between inaccessible and flooded. So you'll sometimes see analysis where it's just the flood area overlaid on the roads. And so that's important, particularly because it tells you that, you know, this right here is a section of road you might need to raise or elevate in order to be able to get over it. But the inaccessibility is showing what portions of the road you can't get to. So for example, in this road here, although these roads are not underwater at this flood level, right? So all these houses, their road is fine. This part of the road is underwater at 1.6 to 2 meters of flooding. So although these roads aren't underwater, you can't get to those neighborhoods. And so this is telling you the people who you're going to have limited access out of their neighborhood, maybe in and out of their neighborhood, getting to work. It also, on a big storm event, could be where emergency responders have difficulty getting into the neighborhood to access them. So this is what the map is showing us. There's also tabs at the bottom where you can download for each locality these inaccessible road summaries. And so this is telling you for all your roads in the locality for Gloucester, at 1.1 meter of flooding, which is 0.3 feet of flooding, you have 592 inaccessible feet. Okay, and so this goes through every 0.1 meter. And then there's many, many pages to this document. So this is the first page, is a summary of all the roads in the locality. But as you get further down into the document, it's going to tell you for each road how many feet are inaccessible at each water level. You can also overlay social vulnerability indices, the FEMA flood zones you can overlay onto the roads, building footprints and parcels, so you can see how many buildings are actually in the area which would be affected. You can see how many parcels are also in the area which may be affected. Okay, so moving on to septic issues, excuse me. The septic concerns are of course showing up a little bit before the flooding. So I said we can see where parcels flood, but that there are some issues that predate that. So septic fields, your general typical septic field is supposed to be separated above the water table. So you want the water table to be at least 3 feet below the ground surface when you put in a drain field. As sea level rises, the groundwater rises also. So this is actually the first impact that you're going to get in a lot of areas, is the groundwater coming up. So septic systems are going to fail before the property itself is routinely flooding. Okay, so this is a project we did for the Virginia Department of Health. This is the Virginia Wastewater Data Viewer. And we took data from the Virginia Department of Health. So these are permit repairs. So these are places where septic systems have failed and have been repaired. And we did an analysis that said, okay, if we were to look in any one of these grids, which is a 1 kilometer by 1 kilometer grid, how often do septic systems fail in this grid compared to the surrounding areas? So the 3 that we are really interested in is these 3 dark colors here. So these are our consecutive hotspots, our intensifying hotspots, and our persistent hotspots. So these are areas where over a 9-year period, either septics failed more often in that grid than the surrounding grids every year, or where at the beginning of the 9 years, they didn't fail as any more often than the areas around them. But by the end of the 9 years, they failed more often than the areas around them. The other one we see a lot of are sporadic hotspots. And so these are areas where in some years, the septic systems in that area tend to fail more than the surrounding areas, and in other years, they don't. And so this can be driven by fluctuating groundwater tables from waters with years with high sea level and high precipitation. These are also, and this is the difficulty, can be driven by areas where there's a cluster of houses that are older, say pre-1960, and all their septic systems are failing at the same time. The other thing I'm showing you right here, there's a number of different things you can put on sewer lines, parcel or building addresses. I'll show you that in a minute, and social vulnerability data. And then this is, these blue things are areas that are not 3 feet above mean sea level. Okay, so I said we need that separation, that 3-foot separation, really to be sure that our septic systems are working. So the dark blue is areas that are currently not 3 feet above mean sea level. So dark blue is areas where we would expect septic systems not to be working right now. Light blue is, or medium blue is, where in 2040 we would expect them not to be working. And light blue is where by 2080 we would expect them not to be working. Okay, so I'm just zooming in here in the Middle Peninsula. You can see we have some areas where we have sporadic hotspots, so areas where some years we get more than others. And then we have some areas where we have these persistent hotspots where we're seeing year after year that the failures, septic failures in these areas are higher than other areas. And I just wanted to zoom into Deltaville. This is a little hard to see, but if you can see these little purple dots. So these are all the building address points in there. And so what we can see is that there are a couple, not many, there are a couple of building address points where they're already within 3 feet of mean sea level, the ground surface elevation. So we might be concerned about those septic systems already. But more importantly, we can see that by 2080, there are a lot of areas where we would be concerned about septic systems working. Okay, so well water concerns. are difficult to predict. We can predict areas where we expect that there could be problems. However, there is a lot of geologic fracturing along the Middle Peninsula coastline. So what this means is that I've had talked to two neighbors where they both have wells the same depth, and one of them has had salinization issues. They've had saltwater coming into their wells, and one of them has not. So one of them had to redig their well, one of them didn't. So this is one of the areas where, although we can predict areas where you might want to be concerned about your well water and monitor it, you really need to get your well water tested. And Elizabeth Andrews is going to give you some resources to do that. So this is all right now from the Northern Neck. So, you know, this is less exciting to you all, but I just want to show you what's we've been working with DEQ to just make a database of where all the wells in the Northern Neck exist. And these orange dots, which you see everywhere, are from an old database that the Northern Neck PDC put together in 2000 that is a record of all of the wells that exist. The colored dots come from a variety of different data sets, but the colored dots are the ones that are in the Virginia Department of Health and Virginia DEQ's databases. So those colored dots are the only ones where we actually know the depth of the wells. So you can see our databases don't have a lot. They have mostly the newer wells in them. So they don't have a lot of the older wells, which means this is an area where we really need to focus more efforts on understanding what our issues are. However, if we look at these are USGS monitoring wells data. So if we look at them, the light blue colors are, you know, tiny, tiny, tiny bits of salinity, essentially none. And the dark red has more salinity. And what we can see is broadly, the dark red areas tend to occur right along the coastline. So these are the areas we would be most concerned about salinization occurring in the Northern Neck. This is true in the Middle Peninsula. But again, remember, see, we have these blue ones next to these red ones. I said there's a lot of fracturing along the coastline here. So there really is a case-by-case kind of basis. This other analysis we have here shows us which of the wells from that previous data set. So we have over 10,000 wells identified in the Northern Neck, over 14,000 wells identified in the Northern Neck. Of those 14,000, which ones are in a FEMA floodplain where they might be, and so those are the yellow ones, where they might be actually overtopped during a storm event. And the blue ones are the ones which are in a slosh model. So that's another storm surge model. If a Category 4 hurricane came through, how many wells are areas where they would be overtopped? Okay, so one of the things we are working on right now for an ongoing NOAA grant is to take all this risk information and put it together, both into a single index, but also where it's more separated out so you can see what is causing the risk. So these are hydrologic units. So these are small, tiny watersheds throughout the state. And so if we look at the FEMA flood risk, so how many houses are within the floodplain, the FEMA floodplain. So the yellow colors indicate there's a lot, and the purple colors indicate there's not very many. If we look at how many miles of road we expect to flood by 2050, again, the yellow colors indicate a lot, and the purple colors indicate not very many. This is the number of septic failures within that HUC unit, within that watershed. So how many septic failures do we have? These are, well, how many permitted repairs really of septic failures do we have? And so again, these high areas are the yellow, and then the purple are low areas. And then the last is the private wells. And this one really is, you know, an estimate of where we might expect to see problems with private wells, where we have private wells that we might expect to have issues. And then if we put it all together, what we get is a sort of total vulnerability index that tells us where the yellow colors basically have risk for all 4 of these concerns. And the purple colors have risks for none of those concerns, and the colors in between have some concerns that they're at risk for. And then part of this grant is to work with a few localities to really look at this on a very detailed, high-resolution area and to help figure out solutions that work for the locality. And then the Virginia VCPC is going to be helping to identify policy and legal barriers for those localities. Okay, so last I'm just going to talk really quickly about natural resources, and if you want to know what's going on with your natural resources, this is WetCat, which is a collaboration with DEQ funded by EPA, and it's to look at the vulnerability of marshes that actually started non-tidal, but we do have a tidal marsh vulnerability assessment that is in there. And it says for 2050 or 2100, so you can pick which layer you want on. It gives a score to each marsh for how vulnerable it is. So that is how likely it is to migrate and how likely it is to erode. So basically, how likely is it to either maintain or expand its extent, or how likely is it to get smaller over time? So these light pink colors are marshes which are most likely to expand and or maintain their size over time. So these are areas where we expect a lot of marsh migration to occur, and also areas up in these embayed areas where you just don't get as much erosion as you do on the waterfront. So these are prime targets for conservation, particularly as marshes become more important for water implementation planning and that kind of thing. So improving water quality. This will help give some idea of where you might expect your marshes to persist and where conserving land would help those marshes to exist longer, and areas where we think the marshes, so these are moderately vulnerable, and these are particularly susceptible to erosion, but this area here is also quite high, so there's not much opportunity for them to migrate. And 2 other tools that are focused on natural resources, but on the benefits that they provide to localities. So this is restoration opportunities of places where living shorelines could go in, but also provide a lot of co-benefits. So they provide habitat, water quality improvement, that kind of thing. So you can zoom in and see where these actually fall along the shoreline. And then this is rank of natural and nature-based features. So these can be forests, they can be marshes, they can be any kind of natural feature that help provide flood reduction benefits to coastal buildings. So they're in a position to intercept overland water flow. And if you click on a particular feature, it'll tell you what it is. So this one I clicked on, it says it's a tidal marsh. There's a fact sheet you can open to learn more about the benefits. But this tidal marsh is given a high rank to mitigate coastal flooding. It protects 12 buildings, so it can intercept like wave energy going to 12 buildings. There are no critical facilities behind it though, so those 12 buildings don't include any critical facilities. And it also is ranked high for incentive programs due to its water quality benefits. And then I just wanted to tell you about a new effort we are just starting where we need the help of people from the localities. So this is being done with the Virginia Department of Health. And the concern is when we need to allocate funding or efforts into a particular area, there's an interest in targeting socially vulnerable areas. However, in rural areas, census blocks are really big. And so sometimes you have a really vulnerable town or community, which is smaller than, much smaller than a census block. And then there are communities within that census block that are not vulnerable at all. And so the whole census block can come out as being ranked not vulnerable. So this is actually a survey. This is not going to be posted on Adapt.va. So this is really for state agencies to use, but we need localities and people with Virginia Department of Health and that kind of thing to help fill out the survey. So you would go in and you can actually like draw an area around a community, and then you can check why it's vulnerable. And then this gives a database that can be used for targeting efforts. So at the very beginning, I said one of the issues in rural localities is that because all of the infrastructure like septic and well are privately owned, it typically falls, and a lot of times access roads actually are privately owned too. Dealing with flooding issues typically falls on the property owner. So trying to target bigger efforts into these communities requires actually knowing where they are. So if you are interested in helping with that, please email me. My email is molly@vims.edu.